Jupiter is the fifth planet from the Sun and the largest in the solar system. It is a gas giant with a mass more than 2.5 times that of all the other planets in the solar system combined, but slightly less than 1,000th the mass of the Sun. Jupiter is the third brightest natural object in the Earth's night sky after the Moon and Venus, and it has been observed since prehistoric times. It was named after the Roman god Jupiter, the king of the gods. Jupiter is primarily composed of hydrogen, but helium constitutes 1/4 of its mass and 1/10 of its volume. It probably has a rocky core of heavier elements, but, like the other giant planets in the solar system, it lacks a well-defined solid surface. The ongoing contraction of Jupiter's interior generates more heat than it receives from the Sun. Because of its rapid rotation, the planet's shape is an oblate spheroid. It has a slight but noticeable bulge around the equator. The outer atmosphere is divided into a series of latitudinal bands, with turbulence and storms along their interacting boundaries. A prominent result of this is the Great Red Spot, a giant storm which has been observed since at least 1831. Jupiter is surrounded by a faint planetary ring system and a powerful magnetosphere. Jupiter's magnetic tail is nearly 800 million kilometers, 5.3 astronomical units, 500 million miles long, covering nearly the entire distance to Saturn's orbit. Jupiter has 80 known moons and possibly many more, including the 4 large moons discovered by Galileo Galilei in 1610. Io, Europa, Ganymede, and Callisto. Io and Europa are about the size of Earth's moon. Callisto is almost the size of the planet Mercury, and Ganymede is larger. Pioneer 10 was the first spacecraft to visit Jupiter, making its closest approach to the planet in December 1973. Jupiter has since been explored by multiple robotic spacecraft, beginning with the Pioneer and Voyager flyby missions from 1973 to 1979, and later with the Galileo orbiter in 1995. In 2007, the New Horizons visited Jupiter using its gravity to increase its speed, bending its trajectory en route to Pluto. The latest probe to visit the planet Juno entered orbit around Jupiter in July 2016. Future targets for exploration in the Jupiter system include the probable ice-covered liquid ocean of Europa. In both the ancient Greek and Roman civilizations, Jupiter was named after the chief god of the divine pantheon. Zeus for the Greeks and Jupiter for the Romans. The International Astronomical Union (IAU) formally adopted the name Jupiter for the planet in 1976. The IAU names newly discovered satellites of Jupiter for the mythological lovers, favorites, and descendants of the god. The planetary symbol for Jupiter descends from a Greek zeta with a horizontal stroke as an abbreviation for Zeus. Jove, the archaic name of Jupiter, came into use as a poetic name for the planet around the 14th century. The Romans named the 5th day of the week Dis Iovis, Jove's day, after the planet Jupiter. In Germanic mythology, Jupiter is equated to Thor, whence the English name Thursday for the Roman dies Jovis. The original Greek deity Zeus supplies the root xeno, used to form some Jupiter-related words, such as xenographic. Jovian is the adjectival form of Jupiter. The older adjectival form jovial, employed by astrologers in the Middle Ages, has come to mean happy or merry, moods ascribed to Jupiter's astrological influence. Jupiter is believed to be the oldest planet in the solar system. Current models of solar system formation suggest that Jupiter formed at or beyond the snow line, a distance from the early sun where the temperature is sufficiently cold for volatiles, such as water, to condense into solids. The planet began as a large solid core, then accumulated its gaseous atmosphere. As a consequence, the core must have formed before the solar nebula was fully dispersed after 10 million years. Over about 1 million years, Jupiter's atmosphere gradually expanded until it had 20 times the mass of the Earth. The orbiting mass created a gap in the solar nebula, and thereafter the planet slowly increased to 50 Earth masses over 3 to 4 million years. According to the grand tack hypothesis, Jupiter began to form at a distance of roughly 3.5 astronomical units, 520 million kilometers, 330 million miles from the Sun. As the young planet accreted mass, interaction with the gas disk orbiting the Sun and orbital resonances with Saturn caused it to migrate inward. This upset the orbits of several super-Earths orbiting closer to the Sun, causing them to collide destructively. Saturn would later have begun to migrate inwards too, much faster than Jupiter, until the two planets became captured in a 3 to 2 mean motion resonance at approximately 1.5 astronomical units, 220 million kilometers, 140 million miles from the Sun. This changed the direction of migration, causing them to migrate away from the Sun and out of the inner system to their current locations. All of this happened over a period of 3 to 6 million years, with the final migration of Jupiter occurring over several 100,000 years. Jupiter's departure from the inner solar system eventually allowed the inner planets, including Earth, to form from the rubble. There are several problems with the grand tack hypothesis. The resulting formation timescales of terrestrial planets appear to be inconsistent with the measured elemental composition. It is likely that Jupiter would have settled into an orbit much closer to the Sun if it had migrated through the solar nebula. Some competing models of solar system formation predict the formation of Jupiter with orbital properties that are close to those of the present-day planet. Other models predict Jupiter forming at distances much farther out, such as 18 astronomical units, 2.7 billion kilometers, 1.7 billion miles. Based on Jupiter's composition, researchers have made the case for an initial formation outside the molecular nitrogen into snow line, which is estimated at 20 to 30 astronomical units, 3.0 to 4.5 billion kilometers, 1.9 to 2.8 billion miles from the Sun, and possibly even outside the Argand snow line, which may be as far as 40 astronomical units, 6.0 billion kilometers. 3.7 billion miles. Having formed at one of these extreme distances, Jupiter would then have migrated inwards to its current location. This inward migration would have occurred over a roughly 700,000 year time period during an epoch approximately 2 to 3 million years after the planet began to form. In this model, Saturn, Uranus, and Neptune would have formed even further out than Jupiter, and Saturn would also have migrated inwards. Jupiter is a gas giant, being primarily composed of gas and liquid rather than solid matter. It is the largest planet in the solar system, with a diameter of 142,984 kilometers, 88,846 miles at its equator. The average density of Jupiter, 1.326 grams per cubic centimeters, is about the same as simple syrup USP, and is lower than those of the 4 terrestrial planets. Jupiter's upper atmosphere is about 90% hydrogen and 10% helium by volume. Since helium atoms are more massive than hydrogen molecules, Jupiter's atmosphere is approximately 24% helium by mass. The atmosphere contains trace amounts of methane, water vapor, ammonia, and silicon-based compounds. There are also fractional amounts of carbon, ethane, hydrogen sulfide, neon, oxygen, phosphine, and sulfur. The outermost layer of the atmosphere contains crystals of frozen ammonia. Through infrared and ultraviolet measurements, trace amounts of benzene and other hydrocarbons have also been found. The interior of Jupiter contains denser materials by mass. It is roughly 71% hydrogen, 24% helium, and 5% other elements. The atmospheric proportions of hydrogen and helium are close to the theoretical composition of the primordial solar nebula. Neon in the upper atmosphere only consists of 20 parts per million by mass, which is about a tenth as abundant as in the Sun. Helium is also reduced to about 80% of the Sun's helium composition. This depletion is a result of precipitation of these elements as helium-rich droplets, a process that happens deep in the interior of the planet. Based on spectroscopy, Saturn is thought to be similar in composition to Jupiter, but the other giant planets Uranus and Neptune have relatively less hydrogen and helium and relatively more of the next most common elements, including oxygen, carbon, nitrogen, and sulfur. These planets are known as ice giants because the majority of their volatile compounds are in solid form. Jupiter's mass is 2.5 times that of all the other planets in the solar system combined, so massive that its barycenter with the Sun lies above the Sun's surface at 1.68 solar radii from the Sun's center. Jupiter is much larger than Earth and considerably less dense. It has 1321 times the volume of the Earth, but only 318 times the mass. Jupiter's radius is about one-tenth the radius of the Sun, and its mass is 1,000th the mass of the Sun, as the densities of the two bodies are similar. A Jupiter mass mj, or mjup, is often used as a unit to describe masses of other objects, particularly extrasolar planets and brown dwarfs. For example, the extrasolar planet HD 209458b has a mass of 0.69 mj, while Kappa Andromedae b has a mass of 12.8 mj. Theoretical models indicate that if Jupiter had over 40% more mass, the interior would be so compressed that its volume would decrease despite the increasing amount of matter. For smaller changes in its mass, the radius would not change appreciably. As a result, Jupiter is thought to have about as large a diameter as a planet of its composition and evolutionary history can achieve. The process of further shrinkage with increasing mass would continue until appreciable stellar ignition was achieved. Although Jupiter would need to be about 75 times more massive to fuse hydrogen and become a star, the smallest red dwarf may be only slightly larger in radius than Saturn. Jupiter radiates more heat than it receives through solar radiation, due to the Kelvin-Helmholtz mechanism within its contracting interior. This process causes Jupiter to shrink by about 1 millimeters (0.039 inches) per year. When it formed, Jupiter was hotter and was about twice its current diameter. Before the early 21st century, most scientists proposed one of two scenarios for the formation of Jupiter. If the planet accreted first as a solid body, it would consist of a dense core, a surrounding layer of liquid metallic hydrogen with some helium extending outward to about 80% of the radius of the planet, and an outer atmosphere consisting primarily of molecular hydrogen. Alternatively, if the planet collapsed directly from the gaseous protoplanetary disk, it was expected to completely lack a core, consisting instead of denser and denser fluid, predominantly molecular and metallic hydrogen all the way to the center. Data from the Juno mission showed that Jupiter has a very diffuse core that mixes into its mantle. This could have been caused by an impact from a planet of about 10 Earth masses a few million years after Jupiter's formation, which would have disrupted an originally solid Jovian core. It is estimated that the core takes up 30 to 50% of the planet's radius and contains heavy elements with a combined mass 7 to 25 times the Earth. Outside the layer of metallic hydrogen lies a transparent interior atmosphere of hydrogen. At this depth, the pressure and temperature are above molecular hydrogen's critical pressure of 1.3 megapascals and critical temperature of 33 kelvins minus 240.2 grad Celsius, minus 400.3 grad Fahrenheit. In this state, there are no distinct liquid and gas phases. Hydrogen is said to be in a supercritical fluid state. The hydrogen and helium gas extending downward from the cloud layer gradually transitions to a liquid in deeper layers, possibly resembling something akin to an ocean of liquid hydrogen and other supercritical fluids. Physically, the gas gradually becomes hotter and denser as depth increases. Rain-like droplets of helium and neon precipitate downward through the lower atmosphere, depleting the abundance of these elements in the upper atmosphere. Calculations suggest that helium drops separate from metallic hydrogen at a radius of 60,000 kilometers, 37,000 miles, 11,000 kilometers, 6,800 miles below the clouds and merge again at 50,000 kilometers, 31,000 miles, 22,000 kilometers, 14,000 miles beneath the clouds. Rainfalls of diamonds have been suggested to occur, as well as on Saturn and the ice giants Uranus and Neptune. The temperature and pressure inside Jupiter increase steadily inward because the heat of planetary formation can only escape by convection. At a surface depth where the atmospheric pressure level is 1 bar 0.10 megapascals, the temperature is around 165 kelvins minus 108 grad Celsius, minus 163 grad Fahrenheit. The region of supercritical hydrogen changes gradually from a molecular fluid to a metallic fluid, spans pressure ranges of 50 to 400 gigapascals with temperatures of 5,000 to 8,400 kelvins, 4,730 to 8,130 grad Celsius, 8,540 to 14,660 grad Fahrenheit, respectively. The temperature of Jupiter's diluted core is estimated to be 20,000 kelvins, 19,700 grad Celsius, 35,500 grad Fahrenheit, with a pressure of around 4,000 gigapascals. The atmosphere of Jupiter extends to a depth of 3,000 kilometers, 2,000 miles below the cloud layers. Jupiter is perpetually covered with clouds of ammonia crystals, which may contain ammonium hydrosulfide as well. The clouds are located in the tropopause layer of the atmosphere, forming bands at different latitudes, known as tropical regions. These are subdivided into lighter-hued zones and darker belts. The interactions of these conflicting circulation patterns cause storms and turbulence. Wind speeds of 100 meters per second, 360 kilometers per hour, 220 miles per hour are common in zonal jet streams. The zones have been observed to vary in width, color, and intensity from year to year, but they have remained stable enough for scientists to name them. The cloud layer is about 50 kilometers, 31 miles deep, and consists of at least 2 decks of ammonia clouds. A thin, clearer region on top with a thick lower deck. There may be a thin layer of water clouds underlying the ammonia clouds, as suggested by flashes of lightning detected in the atmosphere of Jupiter. These electrical discharges can be up to 1,000 times as powerful as lightning on Earth. The water clouds are assumed to generate thunderstorms in the same way as terrestrial thunderstorms, driven by the heat rising from the interior. The Juno mission revealed the presence of shallow lightning which originates from ammonia water clouds relatively high in the atmosphere. These discharges carry mushballs of water ammonia slushes covered in ice, which fall deep into the atmosphere. Upper atmospheric lightning has been observed in Jupiter's upper atmosphere, bright flashes of light that last around 1.4 milliseconds. These are known as elves or sprites and appear blue or pink due to the hydrogen. The orange and brown colors in the clouds of Jupiter are caused by upwelling compounds that change color when they are exposed to ultraviolet light from the sun. The exact makeup remains uncertain, but the substances are thought to be made up of phosphorus, sulfur, or possibly hydrocarbons. These colorful compounds, known as chromophores, mix with the warmer clouds of the lower deck. The light-colored zones are formed when rising convection cells form crystallizing ammonia that hides the chromophores from view. Jupiter's low axial tilt means that the poles always receive less solar radiation than the planet's equatorial region. Convection within the interior of the planet transports energy to the poles, balancing out the temperatures at the cloud layer. The best-known feature of Jupiter is the Great Red Spot, a persistent anticyclonic storm located 22 degrees south of the equator. It is known to have existed since at least 1831, and possibly since 1665. Images by the Hubble Space Telescope have shown as many as 2 red spots adjacent to the Great Red Spot. The storm is visible through Earth-based telescopes with an aperture of 12 centimeters or larger. The oval object rotates counterclockwise, with a period of about 6 days. The maximum altitude of this storm is about 8 kilometers 5 miles above the surrounding cloud tops. The spot's composition and the source of its red color remain uncertain, although photon-associated ammonia reacting with acetylene is a likely explanation. The Great Red Spot is larger than the Earth. Mathematical models suggest that the storm is stable and will be a permanent feature of the planet. However, it has significantly decreased in size since its discovery. Initial observations in the late 1800 seconds showed it to be approximately 41,000 kilometers, 25,500 miles across. By the time of the Voyager flybys in 1979, the storm had a length of 23,300 kilometers, 14,500 miles, and a width of approximately 13,000 kilometers, 8,000 miles. Hubble observations in 1995 showed it had decreased in size to 20,950 kilometers, 13,020 miles, and observations in 2009 showed the size to be 17,910 kilometers, 11,130 miles. As of 2015, the storm was measured at approximately 16,500 by 10,000. 940 kilometers, 10,250 by 6,800 miles, and was decreasing in length by about 930 kilometers, 580 miles per year. In October 2021, a Juno flyby mission measured the depth of the Great Red Spot, putting it at around 300 to 500 kilometers, 190 to 310 miles. Juno missions show that there are several polar cyclone groups at Jupiter's poles. The northern group contains 9 cyclones, with a large one in the center and 8 others around it, while its southern counterpart also consists of a center vortex, but is surrounded by 5 large storms and a single smaller one. These polar structures are caused by the turbulence in Jupiter's atmosphere and can be compared with the hexagon at Saturn's north pole. In 2000, an atmospheric feature formed in the southern hemisphere that is similar in appearance to the Great Red Spot, but smaller. This was created when smaller, white oval-shaped storms merged to form a single feature. These 3 smaller white ovals were formed in 1939 to 1940. The merged feature was named Oval BA. It has since increased in intensity and changed from white to red, giving it the nickname Little Red Spot. In April 2017, a great cold spot was discovered in Jupiter's thermosphere at its north pole. This feature is 24,000 kilometers, 15,000 miles across, 12,000 kilometers, 7,500 miles wide, and 200 grad Celsius, 360 grad Fahrenheit cooler than surrounding material. While this spot changes form and intensity over the short term, it has maintained its general position in the atmosphere for more than 15 years. It may be a giant vortex similar to the Great Red Spot, and appears to be quasi-stable like the vortices in Earth's thermosphere. This feature may be formed by interactions between charged particles generated from Io and the strong magnetic field of Jupiter, resulting in a redistribution of heat flow. Jupiter's magnetic field is the strongest of any planet in the solar system, with a dipole moment of 4.170 Gauss, 0.4170 milliteslas that is tilted at an angle of 10.31 degrees to the pole of rotation. The surface magnetic field strength varies from 2 Gauss 0.20 milliteslas up to 20 Gauss 2.0 milliteslas. This field is thought to be generated by eddy current swirling movements of conducting materials within the liquid metallic hydrogen core. At about 75 Jupiter radii from the planet, the interaction of the magnetosphere with the solar wind generates a bow shock. Surrounding Jupiter's magnetosphere is a magnetopause, located at the inner edge of a magnetosheath, the region between it and the bow shock. The solar wind interacts with these regions, elongating the magnetosphere on Jupiter's lee side and extending it outward until it nearly reaches the orbit of Saturn. The four largest moons of Jupiter all orbit within the magnetosphere, which protects them from the solar wind. The volcanoes on the Moonio emit large amounts of sulfur dioxide, forming a gas torus along the moon's orbit. The gas is ionized in Jupiter's magnetosphere, producing sulfur and oxygen ions. They, together with hydrogen ions originating from the atmosphere of Jupiter, form a plasma sheet in Jupiter's equatorial plane. The plasma in the sheet co-rotates with the planet, causing deformation of the dipole magnetic field into that of a magnetodisk. Electrons within the plasma sheet generate a strong radio signature, with short, superimposed bursts in the range of 0.6 to 30 MHz that are detectable from Earth with consumer-grade shortwave radio receivers. As EO moves through this torus, the interaction generates alpha waves that carry ionized matter into the polar regions of Jupiter. As a result, radio waves are generated through a cyclotron-Maser mechanism, and the energy is transmitted out along a cone-shaped surface. When Earth intersects this cone, the radio emissions from Jupiter can exceed the radio output of the Sun. Jupiter has a faint planetary ring system composed of three main segments: an inner torus of particles known as the halo, a relatively bright main ring, and an outer Gossamer ring. These rings appear to be made of dust, while Saturn's rings are made of ice. The main ring is most likely made out of material ejected from the satellites Adrastea and Metis, which is drawn into Jupiter because of the planet's strong gravitational influence. New material is added by additional impacts. In a similar way, the moons Thebe and Amalthea are believed to produce the two distinct components of the dusty Gossamer ring. There is evidence of a fourth ring that may consist of collisional debris from Amalthea that is strung along the same moon's orbit. Jupiter is the only planet whose barycenter with the Sun lies outside the volume of the Sun, though by only 7% of the Sun's radius. The average distance between Jupiter and the Sun is 778 million kilometers, 5.2 astronomical units, and it completes an orbit every 11.86 years. This is approximately 2/5 the orbital period of Saturn, forming a near orbital resonance. The orbital plane of Jupiter is inclined 1.30 degrees compared to Earth. Because the eccentricity of its orbit is 0.049, Jupiter is slightly over 75 million kilometers nearer the Sun at perihelion than aphelion. The actual tilt of Jupiter is relatively small, only 3.13 degrees, so its seasons are insignificant compared to those of Earth and Mars. Jupiter's rotation is the fastest of all the solar system's planets, completing a rotation on its axis in slightly less than 10 hours. This creates an equatorial bulge easily seen through an amateur telescope. Because Jupiter is not a solid body, its upper atmosphere undergoes differential rotation. The rotation of Jupiter's polar atmosphere is about 5 minutes longer than that of the equatorial atmosphere. The planet is an oblate spheroid, meaning that the diameter across its equator is longer than the diameter measured between its poles. On Jupiter, the equatorial diameter is 9,276 kilometers, 5,764 miles longer than the polar diameter. Three systems are used as frames of reference for tracking the planetary rotation, particularly when graphing the motion of atmospheric features. System 1 applies to latitudes from 7 degrees north to 7 degrees south. Its period is the planet's shortest, at 9 days 50 minutes 30.0 seconds. System 2 applies at latitudes north and south of these. Its period is 9 days 55 minutes 40.6 seconds. System 3 was defined by radio astronomers and corresponds to the rotation of the planet's magnetosphere. Its period is Jupiter's official rotation. Jupiter is usually the fourth brightest object in the sky after the Sun, the Moon, and Venus, although at opposition Mars can appear brighter than Jupiter. Depending on Jupiter's position with respect to the Earth, It can vary in visual magnitude from as bright as -2.94 at opposition down to -1.66 during conjunction with the Sun. The mean apparent magnitude is -2.20 with a standard deviation of 0.33. The angular diameter of Jupiter likewise varies from 50.1 to 30.5 arcseconds. Favorable oppositions occur when Jupiter is passing through the perihelion of its orbit, bringing it closer to Earth. Near opposition, Jupiter will appear to go into retrograde motion for a period of about 121 days, moving backward through an angle of 9.9 degrees before returning to prograde movement. Because the orbit of Jupiter is outside that of Earth, the phase angle of Jupiter as viewed from Earth is always less than 11.5 degrees. Thus, Jupiter always appears nearly fully illuminated when viewed through Earth-based telescopes. It was only during spacecraft missions to Jupiter that crescent views of the planet were obtained. A small telescope will usually show Jupiter's 4 Galilean moons and the prominent cloud belts across Jupiter's atmosphere. A larger telescope with an aperture of 4 to 6 in 10.16 to 15.24 centimeters will show Jupiter's great red spot when it faces Earth. Observation of Jupiter dates back to at least the Babylonian astronomers of the 7th or 8th century BC. The ancient Chinese knew Jupiter as the Sus star suction and established their cycle of 12 earthly branches based on the approximate number of years it takes Jupiter to rotate around the Sun. The Chinese language still uses its name simplified as when referring to years of age. By the 4th century BC, these observations had developed into the Chinese zodiac, and each year became associated with a Tesus star and god controlling the region of the heavens opposite Jupiter's position in the night sky. These beliefs survive in some Taoist religious practices and in the East Asian zodiac's 12 animals. The Chinese historian Xi Zizong has claimed that Gan Di, an ancient Chinese astronomer, reported a small star in alliance with the planet, which may indicate a sighting of one of Jupiter's moons with the unaided eye. If true, this would predate Galileo's discovery by nearly 2 millennia. A 2016 paper reports that trapezoidal rule was used by Babylonians before 50 BCE for integrating the velocity of Jupiter along the ecliptic. In his 2nd century work, The Almagest, the Hellenistic astronomer Claudius Ptolemaeus constructed a geocentric planetary model based on deference and epicycles to explain Jupiter's motion relative to Earth, giving its orbital period around Earth as 4,332.38 days, or 11.86 years. In 1610, Italian polymath Galileo Galilei discovered the 4 largest moons of Jupiter, now known as the Galilean moons, using a telescope. This is thought to be the first telescopic observation of moons other than Earth's. Just one day after Galileo, Simon Marius independently discovered moons around Jupiter, though he did not publish his discovery in a book until 1614. It was Marius's names for the major moons, however, that stuck: Io, Europa, Ganymede, and Callisto. The discovery was a major point in favor of Copernicus' heliocentric theory of the motions of the planets. Galileo's outspoken support of the Copernican theory led to him being tried and condemned by the Inquisition. During the 1660s, Giovanni Cassini used a new telescope to discover spots and colorful bands in Jupiter's atmosphere, observe that the planet appeared oblate, and estimate its rotation period. In 1692, Cassini noticed that the atmosphere undergoes differential rotation. The Great Red Spot may have been observed as early as 1664 by Robert Hooke and in 1665 by Cassini, although this is disputed. The pharmacist Heinrich Schwabe produced the earliest known drawing to show details of the Great Red Spot in 1831. The red spot was reportedly lost from sight on several occasions between 1665 and 1708 before becoming quite conspicuous in 1878. It was recorded as fading again in 1883 and at the start of the 20th century. Both Giovanni Borelli and Cassini made careful tables of the motions of Jupiter's moons, which allowed predictions of when the moons would pass before or behind the planet. By the 1670s, Cassini observed that when Jupiter was on the opposite side of the Sun from Earth, these events would occur about 17 minutes later than expected. Ulmer deduced that light does not travel instantaneously, a conclusion that Cassini had earlier rejected, and this timing discrepancy was used to estimate the speed of light. In 1892, E. Barnard observed a fifth satellite of Jupiter with the 36-inch 910 mm refractor at Lick Observatory in California. This moon was later named Amalfi. It was the last planetary moon to be discovered directly by a visual observer through a telescope. An additional 8 satellites were discovered before the flyby of the Voyager 1 probe in 1979. In 1932, Rupert Wilde identified absorption bands of ammonia and methane in the spectra of Jupiter. 3 long-lived anticyclonic features called white ovals were observed in 1938. For several decades they remained as separate features in the atmosphere, sometimes approaching each other but never merging. Finally, 2 of the ovals merged in 1998, then absorbed the third in 2000, becoming oval Ba. On July 14, 2022, NASA presented images of Jupiter and related areas captured, for the first time, and including infrared views, by the James Webb Space Telescope JWST. In 1955, Bernard Burke and Kenneth Franklin discovered that Jupiter emits bursts of radio waves at a frequency of 22.2 MHz. The period of these bursts matched the rotation of the planet, and they used this information to determine a more precise value for Jupiter's rotation rate. Radio bursts from Jupiter were found to come in 2 forms: long bursts, or L bursts, lasting up to several seconds, and short bursts, or S bursts, lasting less than 1/100th of a second. Scientists have discovered 3 forms of radio signals transmitted from Jupiter. Jupiter has been visited by automated spacecraft since 1973, when the space probe Pioneer 10 passed close enough to Jupiter to send back revelations about its properties and phenomena. Missions to Jupiter are accomplished at a cost in energy, which is described by the net change in velocity of the spacecraft, or delta V. Entering a home and transfer orbit from Earth to Jupiter from low Earth orbit requires a delta V of 6.3 kilometers per second, which is comparable to the 9.7 kilometers per second delta V needed to reach low Earth orbit. Gravity assists through planetary flybys can be used to reduce the energy required to reach Jupiter. Beginning in 1973, several spacecraft have performed planetary flyby maneuvers that brought them within observation range of Jupiter. The Pioneer missions obtained the first close-up images of Jupiter's atmosphere and several of its moons. They discovered that the radiation fields near the planet were much stronger than expected, but both spacecraft managed to survive in that environment. The trajectories of these spacecraft were used to refine the mass estimates of the Jovian system. Radio occultations by the planet resulted in better measurements of Jupiter's diameter and the amount of polar flattening. 6 years later, the Voyager missions vastly improved the understanding of the Galilean moons and discovered Jupiter's rings. They also confirmed that the Great Red Spot was anticyclonic. Comparison of images showed that the spot had changed hue since the Pioneer missions, turning from orange to dark brown. A torus of ionized atoms was discovered along Io's orbital path, which were found to come from erupting volcanoes on the moon's surface. As the spacecraft passed behind the planet, it observed flashes of lightning in the night-side atmosphere. The next mission to encounter Jupiter was the Ulysses solar probe. In February 1992, it performed a flyby maneuver to attain a polar orbit around the Sun. During this pass, the spacecraft studied Jupiter's magnetosphere, although it had no cameras to photograph the planet. The spacecraft passed by Jupiter 6 years later, this time at a much greater distance. In 2000, the Cassini probe flew by Jupiter on its way to Saturn and provided higher resolution images. The New Horizons probe flew by Jupiter in 2007 for a gravity assist en route to Pluto. The probe's cameras measured plasma output from volcanoes on Io and studied all 4 Galilean moons in detail. The first spacecraft to orbit Jupiter was the Galileo Mission, which reached the planet on December 7, 1995. It remained in orbit for over 7 years, conducting multiple flybys of all the Galilean moons and Amalfi. The spacecraft also witnessed the impact of comet Shoemaker-Levy 9 when it collided with Jupiter in 1994. Some of the goals for the mission were thwarted due to a malfunction in Galileo's high-gain antenna. A 340-kilogram titanium atmospheric probe was released from the spacecraft in July 1995, entering Jupiter's atmosphere on December 7. It parachuted through 150 kilometers 93 miles of the atmosphere at a speed of about 2575 kilometers per hour 1600 miles per hour and collected data for 57.6 minutes until the spacecraft was destroyed. The Galileo orbiter itself experienced a more rapid version of the same fate when it was deliberately steered into the planet on September 21, 2003. NASA destroyed the spacecraft in order to avoid any possibility of the spacecraft crashing into and possibly contaminating the moon Europa, which may harbor life. Data from this mission revealed that hydrogen composes up to 90% of Jupiter's atmosphere. The recorded temperature was more than 300 grad Celsius 570 grad Fahrenheit, and the wind speed measured more than 644 kilometers per hour greater than 400 miles per hour before the probes vaporized. NASA's Juno mission arrived at Jupiter on July 4, 2016 with the goal of studying the planet in detail from a polar orbit. The spacecraft was originally intended to orbit Jupiter 37 times over a period of 20 months. During the mission, the spacecraft will be exposed to high levels of radiation from Jupiter's magnetosphere, which may cause future failure of certain instruments. On August 27, 2016, the spacecraft completed its first flyby of Jupiter and sent back the first ever images of Jupiter's North Pole. Juno completed 12 orbits before the end of its budgeted mission plan, ending July 2018. In June of that year, NASA extended the mission operations plan to July 2021, and in January of that year the mission was extended to September 2025 with 4 lunar flybys, 1 of Ganymede, 1 of Europa, and 2 of Io. When Juno reaches the end of the mission, it will perform a controlled deorbit and disintegrate into Jupiter's atmosphere. This will avoid the risk of collision with Jupiter's moons. There is great interest in missions to study Jupiter's larger icy moons, which may have subsurface liquid oceans. Funding difficulties have delayed progress, causing NASA's JIMO Jupiter Icy Moons Orbiter to be cancelled in 2005. A subsequent proposal was developed for a joint NASA ESA mission called EGSM Laplace, with a provisional launch date around 2020. EGSM Laplace would have consisted of the NASA-led Jupiter Europa Orbiter and the ESA-led Jupiter Ganymede Orbiter. However, the ESA formally ended the partnership in April 2011, citing budget issues at NASA and the consequences on the mission timetable. Instead, ESA planned to go ahead with a European-only mission to compete in its L1 Cosmic Vision selection. These plans have been realized as the European Space Agency's Jupiter Icy Moon Explorer JUICE, due to launch in 2023, followed by NASA's Europa Clipper mission, scheduled for launch in 2024. Other proposed missions include the Chinese National Space Administration's Ganymede mission, which aims to launch an orbiter to the Jovian system and possibly Callisto around 2035, and CNS's Interstellar Express and NASA's Interstellar, which would both use Jupiter's gravity to help them reach the edges of the heliosphere. Jupiter has 80 known natural satellites. Of these, 60 are less than 10 kilometers in diameter. The four largest moons are Io, Europa, Ganymede, and Callisto, collectively known as the Galilean moons, and are visible from Earth with binoculars on a clear night. The moons discovered by Galileo, Europa, Ganymede, and Callisto are among the largest in the solar system. The orbits of Io, Europa, and Ganymede form a pattern known as a Laplace resonance. For every 4 orbits that Io makes around Jupiter, Europa makes exactly 2 orbits and Ganymede makes exactly 1. This resonance causes the gravitational effects of the 3 large moons to distort their orbits into elliptical shapes, because each moon receives an extra tug from its neighbors at the same point in every orbit it makes. The tidal force from Jupiter, on the other hand, works to circularize their orbits. The eccentricity of their orbits causes regular flexing of the 3 moons' shapes, with Jupiter's gravity stretching them out as they approach it and allowing them to spring back to more spherical shapes as they swing away. The friction created by this tidal flexing generates heat in the interior of the moons. This is seen most dramatically in the volcanic activity of Io, which is subject to the strongest tidal forces, and to a lesser degree in the geological youth of Europa's surface, which indicates recent resurfacing of the moon's exterior. Jupiter's moons were traditionally classified into 4 groups of 4, based on their similar orbital elements. This picture has been complicated by the discovery of numerous small outer moons since 1999. Jupiter's moons are currently divided into several different groups, although there are several moons which are not part of any group. The 8 innermost regular moons, which have nearly circular orbits near the plane of Jupiter's equator, are thought to have formed alongside Jupiter, whilst the remainder are irregular moons and are thought to be captured asteroids or fragments of captured asteroids. The irregular moons within each group may have a common origin, perhaps as a larger moon or captured body that broke up. As the most massive of the 8 planets, the gravitational influence of Jupiter has helped shape the solar system. With the exception of Mercury, the orbits of the system's planets lie closer to Jupiter's orbital plane than the Sun's equatorial plane. The Kirkwood gaps in the asteroid belt are mostly caused by Jupiter, and the planet may have been responsible for the late heavy bombardment in the inner solar system's history. In addition to its moons, Jupiter's gravitational field controls numerous asteroids that have settled around the Lagrangian points that precede and follow the planet in its orbit around the Sun. These are known as the Trojan Asteroids and are divided into Greek and Trojan camps to honor the Iliad. The first of these, 588 Achilles, was discovered by Max Wolf in 1906. Since then, more than 2,000 have been discovered. The largest is 624 Hector. The Jupiter family is defined as comets that have a semi-major axis smaller than Jupiter's. Most short-period comets belong to this group. Members of the Jupiter family are thought to form in the Kuiper belt outside the orbit of Neptune. During close encounters with Jupiter, they are perturbed into orbits with a smaller period, which then becomes circularized by regular gravitational interaction with the Sun and Jupiter. Jupiter has been called the solar system's vacuum cleaner because of its immense gravity well and location near the inner solar system. There are more impacts on Jupiter, such as comets, than on any other planet in the solar system. For example, Jupiter experiences about 200 times more asteroid and comet impacts than Earth. In the past, scientists believed that Jupiter partially shielded the inner system from cometary bombardment. However, computer simulations in 2008 suggest that Jupiter does not cause a net decrease in the number of comets that pass through the inner solar system, as its gravity perturbs their orbits inward roughly as often as it accretes or ejects them. This topic remains controversial among scientists, as some think it draws comets towards Earth from the Kuiper belt, while others believe that Jupiter protects Earth from the Oort cloud. In July 1994, the comet Shoemaker-Levy 9 comet collided with Jupiter. The impacts were closely observed by observatories around the world, including the Hubble Space Telescope and Galileo spacecraft. The event was widely covered by the media. Surveys of early astronomical records and drawings produced 8 examples of potential impact observations between 1664 and 1839. However, a 1997 review determined that these observations had little or no possibility of being the results of impacts. Further investigation by this team revealed a dark surface feature discovered by astronomer Giovanni Cassini in 1690 may have been an impact scar. The planet Jupiter has been known since ancient times. It is visible to the naked eye in the night sky and can occasionally be seen in the daytime when the sun is low. To the Babylonians, this planet represented their god Marduk, chief of their pantheon from the Hammurabi period. They used Jupiter's roughly 12-year orbit along the ecliptic to define the constellations of their zodiac. The mythical Greek name for this planet is Zeus, also referred to as Dias, the planetary name of which is retained in modern Greek. The ancient Greeks knew the planet as Phaethon, meaning shining one or blazing star. The Greek myths of Zeus from the Homeric period showed particular similarities to certain Near Eastern gods, including the Semitic El and Baal, the Sumerian Enlil, and the Babylonian god Marduk. The association between the planet and the Greek deity Zeus was drawn from Near Eastern influences and was fully established by the 4th century BCE, as documented in the Eponymus of Plato and his contemporaries. The god Jupiter is the Roman counterpart of Zeus, and he is the principal god of Roman mythology. The Romans originally called Jupiter the star of Jupiter Jupiter Stella, as they believed it to be sacred to its namesake god. This name comes from the Proto-Indo-European vocative compound diupter nominative, diaspur, meaning father sky god or father day god. As the supreme god of the Roman pantheon, Jupiter was the god of thunder, lightning, and storms, and appropriately called the god of light and sky. In Vedic astrology, Hindu astrologers named the planet after Brihaspati, the religious teacher of the gods, and often called it Guru, which means the teacher. In Central Asian Turkic myths, Jupiter is called Arendiz or Arents, from ear and of uncertain meaning, and Yalta's star. The Turks calculated the period of the orbit of Jupiter as 11 years and 300 days. They believed that some social and natural events connected to Arent's movements on the sky. The Chinese, Vietnamese, Koreans, and Japanese called it the wood star Chinese. Pinyin, axing based on the Chinese 5 elements. In China, it became known as the year star Suising, as Chinese astronomers noted that it jumped one zodiac constellation each year with corrections. In some ancient Chinese writings, the years were named, at least in principle, in correlation with the Jovian zodiacal signs. In Freyred view of Jupiter, imaged by the Gemini North Telescope in Hawaii on January 11, 2017, Jupiter imaged in visible light by the Hubble Space Telescope on January 11, 2017, ultraviolet view of Jupiter, imaged by Hubble on January 11, 2017, this image of Jupiter and Europa, taken by Hubble on 25 August 2020, was captured when the planet was 653 million kilometers from Earth.